Section 4.3 is on page 320. It talks about the fundamental theorem of calculus. That is one of the most important theorems in this book. And this is what it says. There's two parts to it. Let's get the first part out of the way. Part 1 says, if f is continuous on the closed interval from a to some b, then the function g, which is this integral from a to some x, where x is in that interval, i.e., this function is continuous on those endpoints. That's the only condition. F must be continuous wherever you are integrating, right? And differentiable on the open interval. Then g prime is f of x. What does that mean? That means if you have a g of x, and that happens to be the integral from some a, which is a number to this variable x, of f of t dt. If I was to take a derivative of both sides, if I was to take d dx of both sides, if those match, then this would mean that g prime will equal simply f of t, nothing else. So let me do an example just to elaborate on this. Suppose g equal the integral from a to x. Let's go with numbers. We'll go with variables. Doesn't really matter. You know what? That's fine. A is fine. From a to x of, let's say, t plus 1 dt. So assume that a is right there. If I put x equal t plus 1 starts at 1, rise 1, runs 1. So it's a line that looks like this. Just a straight line. But we're not interested in the whole line. We are only interested from this a to some x. Let's say x is right there. And this right here is going to find this right here, true? That's going to equal, let's see, what is that? That is 1/2 the height times base 1 plus base 2, because that's a trapezoid. That is 1/2 the heights are perpendicular to the bases, right? So there's the height. The height is this distance. If I run from a to x, wouldn't this length be a x minus a? Remember, this is the graph of y equal t plus 1. So when I say x equal a, isn't this a plus 1? That's base 1. And when I say x, if you put an x right there, wouldn't that be x plus 1? So, wouldn't this right here be 1/2 x minus a into a plus x plus 2? So, I got g to equal 1/2 x minus a into a plus x plus 2. And since a is a constant, when I take g prime, leave the 1/2 out of it. Isn't that the product rule? Derivative of the first times the second plus the first times the derivative of the second. Isn't that a 1? Wouldn't that mean g prime would equal 1/2 into a plus x plus 2 plus x minus a? Wouldn't these two cancel out? Wouldn't that be 1/2 into 2x plus 2? And if I distribute that 1/2 in, isn't that x plus 1? That's how it was done. Well, watch. What happens if I apply the fundamental theorem of calculus? What if I take g prime as long as this is continuous on this and t plus 1 is continuous everywhere, this is simply plugging that in. Isn't that x plus 1? And why go through all of that pain? Look at that answer and look at that answer. So the integral could find the area under the curve if f of x is positive. If I take a derivative, this will undo the integral. That's kind of what it's saying. We're going to practice that a bit in the next few problems. Okay, on the first three problems, well, here it is. I'm looking at this. Cosine of t squared is continuous everywhere. So when I take g prime, which is what they want, they say apply the fundamental theorem of calculus part 1. When I take a derivative, that's simply plugging that in. That's the cosine of x squared. And students often ask me, that's it? Well, yeah, that's it. Is that linear? That's u, so that's matching. So what's h prime? So that is, what is the h du? That is, plug that in. That would be the square root of u over u plus 1. What do you have to check? You have to ensure that this is continuous on that interval. This is not continuous at t equal -1, since you're starting at 0, assuming u is positive. This is continuous everywhere, but it doesn't match. I want to use a theorem. I have to make sure that the problem matches the if part identically, the antecedent part. Now that I'm looking at this, I say, well, dr dy, I know you like r prime more, that's negative, and don't you just plug this in for t? Wouldn't that be y cubed, the sine of y? And that's basically it. Actually, that's fine. Next problem is number 14. Well, I notice this is not an x. Well, if it's not an x, and I want to take the derivative of h with respect to x. Well, that's not an x. I could let u equal radical x. And that means now h would become the integral from 1 to u z squared over z to the 4th plus 1, and that becomes a function of u. And when I say take a derivative with respect to x, you'll say, well, okay, but h now depends on u, and by the chain rule, u depend on x. The derivative of this, if I take a derivative with respect to u, well, guess what? That matches the fundamental theorem of calculus. I just plug that in. That is u squared over u to the 4th plus 1. And if I take a derivative of this, that's simply 1 over twice the radical of x. And since I didn't start the problem with a u, I simply want to write the whole thing side by side because I need you to see something. If I put that in there, that would be the square root of x squared and the square root of x to the 4th. I could simplify further. I'm choosing not to, again, for a purpose. I'd like to look at 2 more problems. The same deal here. If I let u equal x to the 4th, then y is now a function of u, no longer of x. And if I say find dy dx, you would say, well, okay, but y now depends on u, and u depend on x. The derivative of this is simply the cosine squared of u, and the derivative of this is 4x cubed, and that would be the cosine squared of u times 4x cubed. And what was u? U was x to the 4th. And the reason I put this side by side, I want you to observe what's going on. If this doesn't happen to be an x, well, I could plug that in. That's right there. Times the derivative of this. Like the chain rule. Remember the chain rule? If this is not an x, I could plug that in, and that's right here. Times the derivative of this. So on number 18, if I want to find dy dx, well, first I notice there's something odd about this. They put it in reverse order. So let's say that is negative the integral from 1 to the sine of x, the square root of 1 plus t squared dt. And if I take dy dx of that, guess what? I really don't need to make all of that. I could just apply the shortcut. That's negative. Plug this in, the square root of 1 plus sine squared of x times the derivative of that by the chain rule. And that's really how we should do this. But if you're ever stuck, you could always use that definition. Fundamental theorem of calculus part 2. And that's all. There are 2 parts. It says if f is continuous on the closed interval, right? That's the part that when I looked at the first definition, I said it only depends on f being continuous. Actually, I meant for part 2, not for part 1. Part 1, it needed to be continuous, and it needed to be differentiable on the open interval. But this is the one that we're going to use the most, more than anything. If f is continuous, and that's the only condition, just f being continuous on this interval, then this is going to be f of b minus f of a, where this capital F is the antiderivative of this. That's from section 3.9. You know, we practiced a bit with this. And I went to section 4.2 and I picked problem number 22. If you remember, I'm going to show you that really quick. 4.2, number 22 was this fun problem, if you remember, right there. That's number 22. Do you remember how we did that problem? Look at that. Remember all that awesome work? We got a -3. Well, guess what? Fundamental theorem of calculus, where are we? Fundamental theorem of calculus says we have another way of doing this. Let us say that is f of 4 minus f of 1, because that is continuous from 1 to 4. What is f of x? So that's really what the answer is. And if I want to find f of x is actually add 1 to the power divided by that, add 1 to the power divided by that, add 1 to the power divided by that. Notice there's no plus c. And the reason for that, I'll play along. If you say plus c, you can. So if you leave it in there, you'll notice something that's going to happen. This is x cubed over 3 minus 2x squared plus 2x plus c. So what is f of 4? Well, f of 4 is 4 cubed, 64 over 3, minus 4 squared, 16, times 2, 32. 2 times 4 is 8 plus c, right? And f of 1, wouldn't that be a 1/3 minus 2 plus c? Well, those cancel out. So I'm really looking at, this is 64 over 3, and those will give you minus 24 plus c, minus f of 1 is 1/3 plus c. And do you see what's going to happen every single time? Those are going to drop off. So normally we will write plus c if this is a definite interval. And 64 over 3 minus 1 over 3 is 63 over 3 minus 24. That is 21 minus 24. And that's how quickly we can get to the -3 instead of what we did on that previous problem. Okay, we can fit one more. I want to tackle problem number 20. I have a lot more, but, well, this is actually f of 1 minus f of -1. And f of x is actually add 1 to the power, divide by that. F of 1 is 1 over 101. And f of -1 is -1 over 101. So this is pretty much 1 over 101 minus a -1 over 101. That turns out to be 2 over 101. And there it is.